Hi Chem 151 students, and welcome to our next video for this week. It is Chapter 19 Part 2, Solubility Equilibria. So now we've already covered acid-base titrations, which was a really huge topic. We started it last week. Our first video of this week was a continuation of that with another example. And now we're going to talk about solubility equilibria, which is generally a smaller topic. We'll also go into formation constants, Kf. So you've started to see some of those in some of your labs, and we're going to define what those are. Now your book goes into a lot of detail on Kfs. I'm going to kind of cover it on a more surface level. And so, but we're going to go pretty deep into solubility. So let's talk about that. So a solubility equilibrium is just one in which the reactant is a solid. So the reactant is a solid, and that's the only reactant. And the equilibrium is for it dissociating into its ions in water. And so if you have a solution here with solid sitting on the bottom, it will dissolve to a certain extent and create some ions. Now some solids, some ionic compounds dissolve very readily in water, others less so. The way you write the equilibrium constant is the same way you write every other equilibrium constant. It's the products over the reactants, but you don't include solids or liquids. So for this reaction here, it's calcium fluoride separating into one calcium ion and two fluoride ions. And so the K for this reaction is going to be, on the top, calcium ions plus the fluoride ions squared, since there's a 2 in front of it. And on the bottom, we have nothing because calcium fluoride is a solid, so it's not included in the equilibrium. And so this K, again, you write it just like any other, but it gets a special name. It's called the solubility product constant. And it's the K for a reaction in which a solid dissolves and separates into its respective ions in water. In general, the equation will look like this. You'll have some metal and a negative ion along with it, and it will separate, creating the subscript here number of metal ions with its charge here, and then the subscript number of the non-metal ions with its charge here. And the KSP is just going to be the metal to its respective coefficient in the balanced equation, times the non-metal ion here to its respective coefficient in the balanced equation. And this K, the K for this reaction is called KSP, the solubility product constant. So the way we measured KSP, so we had a very fancy lab, experiment 6, where we measured the KSP along with the Ka. So we were dealing with two equilibriums there. KSP for calcium iodate rather, and Ka for iodic acid. But if we're just focusing on KSP here, we look here, we would measure the concentration of calcium ions in solution and the measure the fluoride ions in solution in a saturated solution, where as much of the solid has dissolved as could possibly dissolve. And so we have these aqueous ions in equilibrium with the solid on the bottom of the test tube or flask or whatever. So let's say that we have measured these concentrations. So what is the KSP? If we put the solid, we dissolve as much of it as can dissolve in water, and we get equilibrium concentrations of calcium is 2.0 times 10 to the minus 4, and fluoride is 4.1 times 10 to the minus 4. Well, the reaction that's going on is calcium fluoride, solid, is in equilibrium with its aqueous ions. We get one calcium 2+ ion from this, and two fluoride ions, which are -1 in charge. And so the K for this reaction is the calcium concentration times the fluoride concentration squared, and then we do not include the calcium fluoride on the bottom because it is a solid. This will generally be true for all these KSPs. So you just get the stuff in the products. The reactant is always a solid. It's not included in the equilibrium constant. And so now we simply plug in the concentrations that we have measured for each of these. So the calcium ion concentration is 2 times 10 to the minus 4. We'll put that right here. And the fluoride concentration is 4.1 times 10 to the minus 4. We'll put that right here, and we're going to square that. So now we've plugged those in. 2.0 times 10 to the minus 4 for the calcium concentration. 4.1 times 10 to the minus 4 for the fluoride concentration. Now, all we have to do is punch our calculator. We have 2.0 times 10 to the minus 4 times 4.1, which we use our EE, minus 4, and we're going to square that one. And that is equal to the 2 sig figs, 3.4 times 10 to the minus 11. So the KSP is 3.4 times 10 to the minus 11. So that is how you would determine the KSP. If you knew the equilibrium concentrations, you plug them into the KSP expression and get the KSP. So this is the kind of equilibrium problem that's on the easier side to how to get the KSP. So we're given initial concentrations, determine the KSP. We're given equilibrium concentrations, determine the KSP. But there's another type of problem that we've been doing very regularly with equilibrium constants, and that is given the initial concentration and the K, determine the equilibrium concentrations. And so we have a related problem like that with KSPs, which we'll also be doing. Here's some various KSP values for a number of products, or a number of ionic compounds here. Aluminum hydroxide, very insoluble. So like most Ks, a bigger K means more products. In this case, a bigger K means more aqueous ions, so that means higher solubility in general. One important note is you can't compare the solubility directly because each of these would make a different number of ions. So in order to compare solubilities, we do have to actually calculate from the KSP the solubility of each of these compounds. So, but in general, a bigger KSP means the solid is dissolving more. So you can roughly compare them. It's just not, the KSP is not going to directly give you the solubility of the compound because it depends on how many ions are produced. For example, aluminum hydroxide, when it dissolves, will produce 4 ions, 1 aluminum ion and 3 hydroxide ions. However, when barium carbonate dissolves, it will only produce 2 ions, 1 barium ion, 1 carbonate ion. And so you can't compare the KSPs to the solubilities directly, but you can use the KSPs to figure out the solubility. And in general, a higher KSP means more soluble. So for example, with these two, these both produce 2 ions. So we could compare these KSPs directly to determine solubility. But we could not compare the KSP of barium carbonate directly to, for example, calcium fluoride, because calcium fluoride produces 3 ions, 1 calcium, 2 fluoride ions, and barium carbonate only produces 2 ions. So that's going to affect the value of the KSP. And so we would have to actually calculate the solubility of the barium carbonate directly to be able to compare to calcium fluoride, for example. But these are the KSP values for a variety of different ionic compounds. You have a more full listing of KSPs in the appendix. I posted the appendix with all kinds of Ks in last week's module, so you can find them there. So here, how would we calculate the solubility of an ionic compound then? If we want to compare how soluble one ionic compound is to another, as I said, it's not sufficient to just compare the KSPs directly. You would have to determine the solubility of the compound. And so what you'll see is, in terms of this chapter, is a problem stated like this. It will say calculate the molar solubility of some ionic compound at 25 degrees Celsius. That tells you, obviously the equilibrium constant varies with temperature, so the KSP at this temperature is 7.4 times 10 to the minus 11. So you can see that this is a little bit different than most equilibrium problems we're used to. First of all, you're not given an initial concentration. That is because this is a solid dissolving, and so its initial concentration, it's not going to be any concentration. It's just a chunk of solid, and we don't include solids in the equilibria anyway. Also, instead of us asking what is the equilibrium concentration of magnesium ions, or what is the equilibrium concentration of fluoride ions, we're asked what is the solubility. And these things are related. Let's see how they're related. So our equilibrium here is magnesium fluoride solid is dissolving and creating ions. It will create one magnesium ion, which is +2, and two fluoride ions, which are -1. So here, we're gonna do just like we would for any other equilibrium problem. We're gonna set up an ice table. But for our ice table, the amount of magnesium fluoride will not matter because it's solid. What only affects our equilibriums is the aqueous things. And we're starting, before this has dissolved, we're starting with zero magnesium ions, 0 fluoride ions, because we're just with pure water here. Solubility is going to go in the forward direction, of course, so we'll have +X for magnesium, and be careful here, we make 2 fluoride ions, so our change here will be +2X for the fluoride ions. So our equilibrium concentration of magnesium is +X, and it is +2X. Now, an important note, whenever 1 mole of magnesium fluoride dissolves, this produces 1 mole of magnesium ions. So however many moles of magnesium ions were produced, that is how the same amount of magnesium fluoride that dissolved. So when we're calculating the molar solubility of magnesium fluoride, that is going to be equal to X. In fact, your book will often call X, it will say S instead. It will say so in your book will call it S instead of X, big S. S meaning solubility. It's because what we call X here will always be the molar solubility of the ionic compound. The reason why is because we always have a 1 here as the reactant. So if we have X here, X is going to be the amount of magnesium fluoride that dissolved in moles, in molarities, moles per liter. So it is the solubility. Our X is the solubility. So you'll see your book sometimes call X in solubility problems S, because X is the number of moles of the solid that dissolved per liter. So if we figure out X, it is the magnesium ion concentration. It is also the moles of magnesium fluoride that dissolved per liter. So we're looking for X here. X is our molar solubility. So we're now going to write out our equilibrium constant expression. So K is called KSP, and it has a value of 7.4 times 10 to the minus 11. And it is equal to the concentration of magnesium times the concentration of fluoride ions squared. So now we're going to plug in our X values here. So X goes in for magnesium and 2X goes in for fluoride. So we've got X times 2X squared. And this is a situation where you have to be very, very careful with the way that you solve this, okay? Remember your exponent rules. The other way to write this would be X times 2 squared times X squared, okay? So don't forget to square the 2 and the X. So the result is we get 2 squared, which is 4, and then we get X squared times X, which is X cubed. So the KSP here equals 4X cubed. And this is a nice little, neat little thing about solubility problems, is that we never have a denominator here. So we never end up in situations where it is hard to solve for X. We end up just getting straight up, something X to some power. And so we could fairly easily solve for X. And so what we're going to do here is we're going to divide both sides by 4. And then we're going to take the cube root. So we'll take to the 1/3 power. So we're going to do 7.4 times 10 to the minus 11. And we're going to start by dividing by 4. So divide by 4. And then we get 1.85 times 10 minus 11. And then we're going to take the cube root to get x. And so the easier way to do that is just to say to the 1/3 power. So I will use my x to the power, answer to the power of 1 divided by 3. That's the cube root. And so we get 2.6 times 10 to the minus 4. That is x. And that is the molar solubility. Again, it's because when 1 mole of this dissolves, that produces 1 mole of magnesium ions, right? And so however many moles of magnesium ions are produced, that's how many moles of magnesium fluoride dissolved. So the x is the molar solubility in this case. Again, your book often calls x here S. I call it x because I feel like it's confusing to change things midstream. We've been calling this x since the beginning, right? So I continue to call it x, but it is the molar solubility by that reasoning. When 1 mole of this dissolves, you get 1 mole of this, so it's the same. Okay, so that is when we try to dissolve magnesium fluoride in pure water. Now, another type of problem that we dealt with in the equilibrium chapter was dealing with what is known as the common ion effect. And that is equilibrium in which we have a certain amount of product already in the reaction here. So here we're saying now it's a similar problem. Calculate the molar solubility of magnesium fluoride, but instead of in pure water, now it's in a solution of 0.1 molar sodium fluoride. KSP is still the same. So it's the same equilibrium here. We have solid magnesium fluoride dissolving. It makes magnesium 2+ ions and 2 fluoride ions. The difference is that now we have 0.1 molar sodium fluoride. And note again, this is sodium ions and this is fluoride ions. The sodium ions, though, they're spectators. They're not doing anything. So we have 0.1 molar of sodium ions, but we also have 0.1 molar of fluoride ions. And so we're going to have an initial concentration of fluoride ions here that is not 0. So we make an ice table. And for magnesium here, we have 0 amount, but we don't have 0 for fluoride. Our concentration of fluoride is 0.1 molar. Okay. So again, we're going to have plus x here, and we're going to have plus 2x for fluoride. And so we're going to have, for the magnesium concentration, 0 plus x, which is x. And at equilibrium, the fluoride concentration is 0.1 plus 2x. Now, before we actually go and solve for x, we should think about what this means in terms of Le Chatelier's principle, right? So think about that, and we're gonna use that when we compare our answers in the end and see what we got. But you should have that in the back of your mind. What is a reasonable answer, so that once you get it, you can, see if it's reasonable or not. Okay, so now we're going to write the KSP expression. So KSP equals 7.4 times 10 to the minus 11. And that is the magnesium concentration times the fluoride concentration squared because of the 2 here. So now if we plug these in, we have x for the magnesium concentration, and for fluoride we have 0.1 plus 2x, and we're going to square that. So this is one where we could potentially have to solve the quadratic equation if x is too large. So we should double check to see, we should think about, can we use a simplifying assumption? This is going to be important. So we're going to plug this in. We've got x times 0.10 plus 2x squared, and we're going to say that is approximately equal to 0.1 plus 2x is about equal to 0.1. So 2x is very, very small here. Maybe we should do a pre-check just to make sure. So if we're doing a pre-check, we would take our 0.1 pre-check. We're going to divide it by the k, 7.4 times 10 to the minus 11. So our initial concentrated divided by k, is that greater than 400? Yes, it is. It's definitely greater than 400. It's way bigger than 400. So we're okay here. 0.1 plus 2x is going to be about the same as 0.1. When we add x, x is so small, it's not going to change the value of 0.1 very much. And so now we have 7.4 times 10 to the minus 11 equals x times 0.1 squared. If we want to determine x, we have to divide both sides by 0.1 squared. I was trying to draw that. So we divide both sides by 0.10 squared. That's going to cancel here. Divide this side by 0.10 squared. Okay, so the molar solubility is going to be 7.4 times 10 to the minus, not 9, 11, sorry. Got a little ahead of myself there. 11. Save. Divide by 0.1 squared, which is, oops. So 7.4 times 10 to the minus 11 divide by 0.1 squared equals 7.4 times 10 to the minus 9 molar. So that is x, and that is the molar solubility here, right there. And so now let's compare the answer that we got for the solubility of magnesium fluoride in pure water versus in sodium fluoride, where we had the common ion effect. So in molar solubility in pure water was 2.6 times 10 to the minus 4, and in 0.1 molar sodium fluoride, it was 7.4 times 10 to the minus 9. Now we should be thinking, does this make sense? Why does the solubility decrease in the presence of fluoride? Well, it's because if you're adding fluoride ion relative to pure water, that is adding more fluoride ion, which causes the equilibrium to shift to the left, which means lesser solubility of the magnesium fluoride due to the common ion effect. This is bringing back Le Chatelier's principle. So you notice we keep coming back to that because that explains a lot of things about what we observe here. Okay. So that is how to calculate the molar solubility of an ion. Again, remember, a bigger KSP does mean more soluble in general, but in order to compare solubility of one ionic compound to another directly, you do have to do the equilibrium calculation and determine the molar solubility, because for the K, it will depend on how many ions this ionic compound makes. That will really affect the value of the K. So this is just a chart showing the effect of adding more and more fluoride ions. So in pure water, the solubility of magnesium fluoride is, as we determined, 2.6 times 10 to the minus 4. But as we add more and more fluoride ion, that causes the solubility to decrease due to Le Chatelier's principle. Again, adding more fluoride ion shifts the equilibrium to the left, meaning lesser solubility of the magnesium fluoride. Now, that's solubility with respect to the common ion effect. What about other things that could affect solubility? So last week you did experiment 13. This week you're probably working on trying to write your reactions that explain what happened in experiment 13. And so here's where we're going to start to talk about the things that affect solubility in terms of the pH and also the common ion effect, and also in terms of potential ligands and the formation of transition metal complexes. So for some ionic compounds, they will have greater solubility in acid. The way in which they might have greater solubility in acid is if they have a negative ion that is a base. So this contains the calcium ion. The calcium ion is a positive ion that is not particularly acidic. So this is a neutral ion. But it also has the carbonate ion, CO3 2-. Now, the conjugate acid of the carbonate ion is bicarbonate. And this is a very weak acid. It's not even really an acid at all. And so this makes this a decent base. In fact, it's quite a strong base. So the fact that we have carbonate that is dissolving here means that the carbonate can react with the acid and make the bicarbonate ion. And this will remove it from the solution, which will drive this solubility forward. And so basically, the carbonate ions are being removed. So for calcium carbonate, let's write the solubility equation. For calcium carbonate, when it dissolves, it is in equilibrium with calcium ions and carbonate ions. But these carbonate ions go on to react with acid. And so if you add acid to this, this effectively removes carbonate ions. So what is that going to do to this solubility equilibrium? It's going to drive it forward, because we're continuously removing carbonate ions because these are reacting with acid in an acidic solution and making bicarbonate. And so the take-home message here is that if you have a salt that has a basic anion, it will be more soluble in acid than it is in pure water, because the reaction with the acid in this fashion will remove that basic anion. Likewise, if you have a solution with an acidic cation, it will be more soluble in a base, because that base will react with the cation and remove it. Usually, this is in the form of a formation of a transition metal complex. So usually this is stated more in terms of transition metal complexes than in terms of in the same terms we have here with a basic anion. But watch out. So a question I love to ask is, which of the following ionic compounds would be more soluble in acid? And it will be the ionic compound that has the base, or the ionic compound that has the basic anion. That will be more soluble in water. And if you forgot how to determine that, remember, basically a basic anion will be one that is the conjugate base of a weak acid. That's what we talked about at the end of chapter 18. Now, as I said, the formation of complex ions can also affect solubility. So we had a number of acidic cations, and generally those were, transition metal complexes that behave as acids, but the way they behave as acids is as Lewis acids generally. So they basically form complex ions. So any of these transition metal ions could form a complex ion. And so if you add a base such as ammonia or hydroxide, those can react with the transition metal and form a complex. And so notice here we have a silver ion. This can form a complex with amine ligand. Here is showing it just taking one amine ligand. We're going to call the K for this equilibrium K1, and it is about 2100. Then this complex can itself grab another amine ligand and have a diamine silver complex. And so here's a second K for this reaction. Overall, what's happening is the silver is actually picking up one ligand, but then it's going on to pick up a second. So the overall equation is that one silver ion gets two amine ligands, and it makes the diamine silver ion. And we have so this K is called the KF for diamine silver ion. It's the formation of the diamine silver complex ion from its respective transition metal cation and ligands. And so one thing about KF I'll say is, so this is the definition here. It's the formation constant, equilibrium constant for the reaction of transition ions with ligands to form transition metal complex. So a couple of things. Number one, given these two Ks, how could we determine the Kf? This is just a little reminder from chapter 17 as we're getting closer to the next exam, and as we move forward, you may need a reminder here. So the K for this reaction, if we're writing the K, we write it just like any other K, okay? It's products over reactants here. So the product here, the Kf, its expression is the product silver, diamine silver complex over silver ion concentration over amine ligand concentration squared, amine molecule concentration squared. Now, given that we were given two reactions with a K1 for the formation of the silver complex with one amine, and then the formation of its complex from the other, the Kf is these two multiplied by one another, because we added the two equations to get the overall reaction. So the Kf here is, again, the overall K. You can see if we multiply these by one another, the silver cancels, and we end up on top with the monoamine silver cancels, and on top we end up with the diamine silver complex on top. On the bottom we have silver ion, and we have amine molecules squared. So the overall Kf was the initial, the K for the first reaction times the K for the second. Just a reminder, kind of harkening back to the equilibrium chapter, that if you have two separate reactions and you add them together, the K for the overall reaction is the two Ks multiplied together. And so just to show that with the calculator here, 2.1 times 10 to the 3 times 8.1 times 10 to the 3 equals 1.7 times 10 to the 7. Generally, you don't have to do this to figure out the Ks, okay? If you look at the appendix with all the Ks, you'll find some formation constants as well. Those formation constants are given on that table. That said, I don't really have you do equilibrium calculations with formation constants. So they are presented in your book, but I don't go into detail on them. But I do expect you to understand what a Kf is, basically. So if you were given, if I say, what is the Kf for diamine silver complex? Well, that would have diamine silver complex ion on top, and the respective transition metal ion and the ligands to the power of however many there were. So I do want you to know what Kf is, but you don't have to do a lot of fancy Kf calculations like they do in the book. I do expect you to understand, though, how the formation of complex ions will affect solubility from a conceptual standpoint. So let's say we're talking about the solubility of silver chloride. So when it dissolves in water, it produces silver ions and chloride ions. Now, if we put ammonia into this solution, what is this going to do to the solubility of silver? Well, remember, silver ions can form a complex with ammonia. And so if we add ammonia, what we're effectively doing here is we're removing silver ions from, removing them from the solution, because they're going and they're forming this silver complex instead. This is removing silver, but because of the addition of ammonia. And so by removing the silver by its reaction with ammonia, we drive this reaction forward. So silver ions become more soluble in the presence of a base, and we actually use that. We use that property in the experiment 13. For some of these ions, they remained soluble because they produced a ionic compound. For some, they produced neutral compounds with hydroxide, for example, that became insoluble. And so, again, you don't have to do fancy calculations with these, but I do expect you to understand why adding ammonia would increase the solubility of silver chloride. It's because that ammonia is reacting with the silver ions and thus removing them, causing the solubility equilibrium to shift to the right. So we can see here, here's a graph. Silver chloride has a pretty low solubility in pure water, but if we add ammonia, we can increase the solubility of silver chloride due to its removal, the removal of silver ions because of the formation of the diamine silver complex, which drives this solubility equilibrium forward. So again, I'm not going to have you do fancy calculations with solubility in acid or solubility and formation of complex ions. Your book does have some of those in there, but I didn't assign any of them. But I do expect you to understand conceptually why adding a ligand would increase the solubility of a transition metal ion. And often that ligand may be hydroxide. So for many transition metal ions, it will increase the solubility. Adding hydroxide will increase solubility because it will behave like a ligand until it produces an insoluble hydroxide. And so here's an example of that. Silver chloride is not very soluble in water, but if we add ammonia, it will make the formation of the diamine silver complex ion, which will drive the solubility of silver chloride forward because of the removal of silver ions from solution. So you can see that result here. And here are some formation constants for a variety of complex ions. Again, I'm not going to have you be doing equilibrium calculations with Kf, but I do expect you to understand what a Kf is and why transition metals become more soluble when amine or hydroxide ligands are added. Now, there is a proviso to this, and that is that if you do add hydroxide, sometimes an insoluble hydroxide will be formed. And so you'll get a different precipitate, the hydroxide precipitate. However, some of these hydroxides are amphoteric, and we discussed this amphoterism in the transition metal complex chapter as well, chapter 23. So aluminum hydroxide is amphoteric because it's a base, it's a hydroxide. So if you add acid, this will neutralize the base, producing water and aluminum ions, and ions are generally soluble. So the aluminum ions are soluble here. So the aluminum hydroxide becomes more soluble when you add acid. But for some hydroxides, they also become more soluble when you add base. This is because aluminum hydroxide is acting as a base, but in this second equation, aluminum hydroxide is acting as a Lewis acid. It is accepting the ligand hydroxide, accepting the electron pair, thus behaving like a Lewis acid, and it's producing the soluble tetrahydroxoaluminate ion. And not all transition metal hydroxides are amphoteric. You used this fact to your benefit when you were doing your experiment 13 qualitative analysis. You were able to add additional base, which caused, for example, aluminum hydroxide to remain soluble, which was then in another supernatant, which you saved for a later test. But some of the ions remained insoluble, and those ones you kept them as a precipitate and then added various substances, for example ammonia, to dissolve them again to some extent. And so these amphoteric hydroxides, and the fact that aluminum hydroxide in particular can become soluble when added with acid, or become more soluble when more base is added, is an important concept for analyzing your experiment 13 that you did last week. So you observed the aluminum hydroxide precipitate. When you tested for aluminum ions near the end of experiment 13, you saw this gelatinous white precipitate when you added sodium hydroxide to a solution containing aluminum ions. But if you further add additional hydroxide, then this precipitate will dissolve as it forms a tetrahydroxoaluminate ion. So aluminum hydroxide is insoluble but if you add acid and cause the pH to go down, it will make soluble aluminum ions. If you add base, it will and causes the pH to go up, it will make the soluble, here it's the tetrahydroxo aluminate ion, which is an ion, so it's soluble, and over here at the low pH you get the aluminum 3+ ion, which is also soluble. But in the middle it's neutral aluminum hydroxide, which is insoluble. And finally, precipitation of ionic compounds. So there's one last problem having to do with solubilities and KSPs, and those are which you are given a certain amount of concentration of each ion and asked to decide if they will precipitate or not. So this is where you essentially calculate a Q and compare it to K. And so we've been doing this since chapter 17. You know that if Q is greater than K, that means you have too much product, so the reaction has to go backwards. And this would result, backwards means precipitation in this case, in the solubility case. If Q is less than K, that means the reaction will continue to move forward, which in the case of solubility means that more of the solid can still dissolve. So you're not at equilibrium yet, and you won't have precipitation. So again, here for our calcium fluoride example, the KSP is calcium ion concentration times fluoride ion concentration squared, since there's a 2 there. And we can also determine a Q. So remember, Q is the same as K, except that the concentrations don't necessarily have to be equilibrium concentrations. They can be whatever concentrations we happen to have at the time. Now, unfortunately, because for some reason they like to make a new name for everything, the Q for a solubility reaction is called the ion product, or IP. But it's just another Q. It's just a Q with a special name. We're going to compare it to K like we always do, and it's the same thing. Q is less than K, the reaction goes forward. Q is greater than K, the reaction goes backwards. Same old, same old. Just now we're doing it for solubility. So IP is called the ion product. And again, if Q, again, ion product is the Q, right? It's just a Q for solubility. We call this Q. We call it IP, whatever. As long as you understand the concept, okay? If Q is greater than K, that means there's too much dissolved ions, too much product. Remember, Q and K are product over reactant. So in this case, the product is dissolved ions, and the reactant is the solid. So if Q is greater than K, or the ion product is greater than K, that means we have too much of this. Too much dissolved ions. So the reaction will go backwards, and those dissolved ions will precipitate as a solid. If the ion product is equal to K, that means the solution is saturated and we're exactly at equilibrium. And then if Q is less than K, that means that we don't have as many ions as could dissolve. So more are going to continue to dissolve. The solution is not yet saturated, so precipitation will not occur. Now, your book goes into significant detail about separation of ions by selective precipitation with sulfides. And this gives its own special K, which is called the KSPA, solubility product in acid, related to sulfides. So adjusting the pH will change the ion product in the case of those solids, sulfide solids that are dissolved in acid. Your book goes into a lot of detail about that. When it comes to KFs and KSPAs, I'm not going to do calculations with those. So equilibrium calculations that you see related to KF and KSPA, you don't really have to focus on those when in your reading and your textbook. You can kind of skip those. Just make sure that you understand the ideas behind KF and solubility in acid and base. And the parts about the KSPA and the sulfides, you can skip those. I'm not going to go into a lot of detail on those. What I will do though is I can ask you about, hey, if we have this certain concentration of ions, will precipitation happen or not? So what I'm asking you, are we past the solubility equilibrium? Are we not yet there yet? This involves calculating Q and comparing to K. Of course, for solubility, we call Q the ion product, or IP, but it's still Q. Okay, it's the same thing. Just calculate Q compared to K and see which direction the reaction goes, towards more ions dissolving or for the ions not dissolving and making the solid, or the reaction going backwards. We can also separate ions based on their selective precipitation. And you did something like that with lead 2 chloride in your experiment 13. So you heated up a mixture of potentially silver chloride, lead 2 chloride, and the lead 2 chloride was more soluble. So that was able to dissolve while the silver chloride would remain as a solid. And so that was selective precipitation of the two. So here we have a solution that consists of 0.2 molar magnesium chloride and 0.1 molar copper 2 chloride. And we're going to make the insoluble hydroxides by adding hydroxides. But we want to add just enough hydroxide so that one of the ions will separate out, will precipitate out, while the other one is barely precipitating out. And you can see there's a big difference in the solubility between magnesium hydroxide and copper 2 hydroxide. The magnesium hydroxide is significantly more soluble. So what we're going to do is we're going to precipitate out the copper 2 hydroxide while hopefully precipitating out as little as possible the magnesium hydroxide. So we want to know how much it would require to just get to right before precipitation of magnesium hydroxide. How much hydroxide could we add to where copper 2 hydroxide is precipitating out but magnesium hydroxide is not? Okay. And we can compare the KSPs directly to compare the solubilities because they both create 3 ions. So for these, we can compare them directly. Now, magnesium hydroxide, again, has a KSP that is 10 to the 10 times greater. So it's 10 to the 10 times more soluble than copper 2 hydroxide. So we're going to add as much hydroxide as we can to not precipitate the magnesium hydroxide. That should preferentially precipitate out the copper 2 hydroxide. And then we can calculate how much copper 2 hydroxide remains to see how well we were able to separate them by this selective precipitation. So the solubility for magnesium hydroxide is like this. Solid magnesium hydroxide separates into magnesium 2 plus and 2 hydroxide ions. Again, we're trying to precipitate out the magnesium ions with hydroxide. So we're concerned with what is the solubility of the magnesium hydroxide. So its KSP would be magnesium ions times hydroxide ion concentration squared, and that is given as 6.3 times 10 to the minus 10. This is given to us. Now for the copper 2 hydroxide, it's copper 2 ions, again, those 2 hydroxide ions, so the KSP is copper concentration times hydroxide concentration squared, and that is 2.2 times 10 to the minus 20. So we're going to focus here on the magnesium hydroxide because we can add a lot of hydroxide, or not a lot, but we can add more hydroxide before the magnesium hydroxide precipitates, while the copper 2 hydroxide will be precipitating because it's less soluble. And we're trying to precipitate out as much copper 2 hydroxide as possible without precipitating any magnesium hydroxide. So we're going to figure out how much hydroxide we could add to be at equilibrium for magnesium hydroxide. So we're going to solve this for the hydroxide concentration. So what we're going to do is we're going to divide each of these or we're going to divide both sides by the magnesium 2+ concentration. I'm going to cancel that, and so we'll get hydroxide concentration squared equals 6.3 times 10 to the minus 10 over the magnesium ion concentration. And then to find the concentration of hydroxide, that is the maximum amount we could add, the amount that would be at equilibrium but not past it, we'll take the square root of both sides. So the hydroxide concentration is the square root of 6.3 times 10 to the minus 10 over the magnesium ion concentration, which were given in the previous slide. Let's go back and look at that. Magnesium ion concentration is 0.2 molar. Chloride concentration is 0.4 molar, twice this, but we don't care about the chloride, it's just a spectator. So this right here is 0.20 molar. So we're going to calculate how much hydroxide we could add to get right up to equilibrium, but not past it. That's what we solved for here. So hydroxide concentration is going to be the square root of the KSP divided by the magnesium concentration. The KSP was 6.3 times 10 to the minus 10, and the magnesium ion concentration was 0.2 molar. So let's calculate that now. So the hydroxide concentration at perfect equilibrium with, when just the right amount of solid has been added, just right, the equilibrium amount of solid has dissolved, so none will precipitate. It will be 6.3 times 10 to the minus 10 divide by 0.2, and we're going to take the square root of that, and we get that at equilibrium here the concentration of hydroxide is 5.6 times 10 to the minus 5 molar. So again, just going back, we're figuring out how much hydroxide we could have to be exactly at equilibrium. We can go back and plug this in to make sure it equals the K, right? So if we were calculating K, it would be the magnesium concentration, which was 0.2 molar, times the hydroxide concentration, 5.6 times 10 to the minus 5, and we'd square that. So here we're right at equilibrium, 6.3 times 10 to the minus 10. So if we're at the point where if we added any more hydroxide, our Q would be greater than K and precipitation would happen. Right now, for what we calculated, this is where Q equals K. If we add 5.6 times 10 to the minus 5 molar concentration of hydroxide, we will be right at equilibrium. Any more hydroxide added and Q will be greater than K, and magnesium hydroxide will start to precipitate. So this is the maximum amount of hydroxide we could add without precipitating magnesium hydroxide. Now let's see how much copper ion is left over, assuming that we put in this much hydroxide. It should be very little, because the copper 2 hydroxide is significantly less soluble than the magnesium hydroxide, so much of it must have already precipitated out. So we're going to now solve this for the copper concentration. To solve this for the copper concentration, we're going to divide both sides by the hydroxide concentration squared. That will cancel, and then we'll have the copper concentration is the hydroxide ion concentration. So the copper concentration will be KSP divided by the hydroxide concentration squared. So this is the maximum amount of hydroxide that will not precipitate magnesium. Let's calculate copper 2 concentration remaining with this much hydroxide. So again, copper 2 concentration will be the KSP over the hydroxide concentration squared. So the KSP is 2.2 times 10 to the minus 20. And the hydroxide concentration is the amount we added, 5.6 times 10 to the minus 2. And so let's see how much copper was left in solution. And so it will be 2.2 times 10 to the minus 20 divided by 5.6 times 10 to the minus 5 squared. And we get 7.0 times 10 to the minus 12 molar. So very, very little copper ion concentration remaining. remember it was originally, if we go back to the original problem here, it was 0.1 molar copper ions. But now, if we have this much hydroxide, there will only be 7.0 times 10 to the minus 12 molar of copper ions remaining. And there will still be 0.2 molar of the magnesium ions. So we have effectively separated the magnesium ions and the copper ions by precipitating out the copper 2 hydroxide and adding just enough hydroxide that the copper 2 hydroxide would precipitate out, but the magnesium ions would not. Okay. And so again, if we wanted to do this with Q, we just calculated Q. So at this concentration of hydroxide, the Q for the magnesium, so Q for the magnesium reaction was magnesium 2 plus concentration times hydroxide concentration squared. That Q was 0.20 molar times 5.6 times 10 to the minus 5 squared, and of course that was equal to K because we set it up to be exactly that. I calculated it earlier, but one more time, 0.2 times 5.6 times 10 to the minus 5 squared. And of course Q equals K, 6.3 times 10 to the minus 10. So with our initial concentration of magnesium and the concentration of hydroxide we reacted, we're right at equilibrium. So again, if we added any more hydroxide, magnesium hydroxide would begin to precipitate. But since Q equals K, or IP equals K, we are at equilibrium. Now let's calculate the Q for the copper at this concentration of hydroxide. So the Q for the copper reaction would be copper 2 plus. I'm gonna calculate that somewhere else. I'll calculate it at the top. So Q for the or on the left here, I have plenty of room. Q for the copper reaction would be copper 2 plus concentration times hydroxide concentration squared. And these are not equilibrium concentrations. These are the concentrations we have right now. So we have 0.10 molar of copper ions, which is what we started with, and hydroxide concentration is 5.6 times 10 to the minus 5, and we're going to square that. Okay, so we calculate that, 0.1 times 5.6 times 10 to the minus 5 squared, and we get 3.1 times 10 to the minus 10. Now here Q is greater than K because the K for the copper 2 hydroxide was 2.2 times 10 to the minus 20. Q is far greater than K, so of course we've got significant precipitation here. What this means is Q is greater than K, the reaction goes backwards here. So for this reaction, Q equals K, the reaction doesn't go forward or backwards, it does not precipitate. But here Q is greater than K, so the reaction is going to go backwards, which will result in precipitation. And so that's it for our lecture on solubility equilibria, and this wraps up chapter 19. And so next week, so as you'll notice, this is the last lecture for this week. So there's not going to be any more lecture. What I'm trying to do is make sure that at the end of this week and the beginning of next week that you're practicing chapter 19 problems. You should do more than the homework. So I don't want to, slam you over the head with lecture, but I did get this all done early so that we could have time to prepare and practice before the exam. You need plenty of time to practice these problems. Next week, I'll do some more practice problems with you, and also I'm going to begin a lecture on chapter 20, which won't be on the exam, but this is going to leave us a little bit of time near the end so we're not too crunched up near the end, and we have a little bit of time for review before your big final exam. So that's it for lecture this week. Good luck on your homework, and make sure to come to office hours and let me know if you need help on anything, including homework or additional book problems that you're working on in preparation for the exam coming in a couple weeks. Okay, and I'll see you next time. Have a good one.